Okay, we're looking at the wave equation. Many people try to solve this equation using separation of variables. We're going to do something else. We're going to derive D'Alembert's formula, okay? So first I'm going to write the equation in differential operator form, where essentially I just look at the derivatives which are acting on u. So this is just the definition of the equation. Now I look at this operator as a second order differential operator, but it has a nice form of a squared minus b squared, so I can factor it. And this uses the fact that partial derivatives commute. In factoring this expression, I get the following equation, where I have two directional derivatives acting on u. The first is a directional derivative in space-time in the direction 1c. And then this outer derivative is again a directional derivative where I identify this operator as the gradient operator dotted with the direction 1 minus c. So if I look at the outermost differential operator and it acts on this function, what this equation says is that the directional derivative in the direction 1 minus c of this quantity is 0. In other words, this quantity is constant in the direction 1 minus c in space-time. Okay? So what that means is that this is only going to be function which depends on x plus ct. Where notice that x plus ct is forms a line in space-time with direction 1c, direction c1, my first coordinate is time. So this is just tx dotted with this direction c1, which forms a line, and notice that the direction of this line is exactly orthogonal to the direction of this directional derivative. Namely, the vector c1 is orthogonal to the vector 1 minus c. So what this is saying essentially is that my only non-trivial dependence is in the direction c1, and I'm constant in the direction 1 minus c, which is exactly the statement that this directional derivative should vanish. Okay? Now we do the same trick again, where now I look at this directional derivative, which is again in the direction 1c, and I recognize that this is a differential equation which tells me that my function u in the direction 1c, I have dependence of the form x plus ct. Okay, so basically this derivative gives me information about the way that u varies in the direction 1c, and it's telling me that u varies as a function of x plus ct in this direction. Now I could have non-trivial dependence in the other direction, which is why we end up with the general solution of the form f of x plus ct due to the dependence in this direction, and then g of x minus ct, where x minus ct is the vector minus c1. This is dependence in the direction of the vector minus c1, which is exactly orthogonal to the direction of this directional derivative. Okay? So this dependence is coming from this equation, and the dependence on x minus ct is coming from the fact that this derivative only encodes the behavior in the direction 1c, and so we could have non-trivial dependence in the direction minus c1. Now, One thing I should note is that these functions are not actually the same from line to line, so perhaps it is clearer if I just use the letter h. These functions are not actually the same. The point is they only depend on x plus ct. Okay? Wonderful. So this is the heart of the solution. And now once we have this, I'm going to write u of x and t is some h of x plus ct plus g of x minus ct. So with this in hand, I can now just plug in my initial data. I get u of x0 is h of x plus g of x, and ut of x0 is, if I take the time derivative, this c comes out h prime, and then evaluate at t equals 0, h prime of x, minus c g prime of x, where again, taking the time derivative of this quantity, the minus c pulls out by the chain rule, and then I evaluate the derivative at t equals 0 to give me g prime of x. And so, by assumption, this of our initial data, this is equal to f of x, and this second line here is equal to g of x. Okay, so let's massage this second equation here real quickly. So if I integrate from 0 to x, so I guess let me write this more clearly. So the second equation is going to become c times the derivative of h minus g is equal to our function little g, where these are all functions of x. And so now I have just a derivative on the left-hand side, so I can just integrate the equation and use the fundamental theorem of calculus. Let's first divide over the c and then integrate. So I have h minus g of x is equal to the integral from 0 to x of 1 over c g of t dt. And this just follows from integrating this equation. Okay? Okay, so now I have two equations for h and g. Let's write them explicitly. So I'll start here. Okay, so I have h plus g. I'm going to omit the x dependence now is f, and h minus g is the integral from 0 to x, 1 over c g of t dt. Okay, and this I should say is maybe f of x. Okay. So now if I add these two expressions, I can solve for h, and I get that h of x is equal to f of x plus integral from 0 to c, 0 to x, 1 over c, g of t dt. And then if I take this expression and subtract the second expression from it, I get that, and this should be a 2, excuse me, I get that 2 times g of x is equal to f of x minus the integral from 0 to x, 1 over c, g of t dt. And now I realize that t is a terrible integration variable because we're using t. So let me change the t to, let's say, c. So this is my variable of integration. I don't want this to actually, this isn't related to time. So I apologize for the notational error there. Okay, we're almost done now, because now we just plug back in to our original general solution, h, but instead of x, I've solved for h of x. I want to plug in x plus ct everywhere I see an x in this equation. So I get that u of x and t is a 1/2 dividing by 2 over here. I have 1/2 f of x plus ct plus 1/2 integral of, and I'll bring out the c, 1 over 2c, integral from 0 to x plus ct, g of c dc, and then I add my g of x, which is 1/2 f of x minus ct plus 1 over 2c, and this is not a plus but a minus sign, 1 over 2c, integral from 0 to x minus ct of g of c dc. Now, of course, we should make sure that we only define this for x and t such that this expression is, or actually, no, this is fine. This is fine. And now, now this minus sign over here, I can use that to flip the bounds of integration. And then just bring these two integrals together, right? I have an integral from x minus ct to 0, and then an integral from 0 to x plus ct. And so I get 1/2 f of x plus ct plus f of x minus ct plus 1 over 2c integral from x minus ct to x plus ct of g of c dc. And this is the D'Alembert's formula that more often than ever should be the case is just handed to students. And hopefully you now understand a little bit more where it comes from.